Contrary to a simple cause and effect universe, Einstein's strange mathematics revealed that the fabric of spacetime could tear, leading to cosmic dead ends and one-way passages. His field equations don't just describe gravity, they permit the existence of black holes as cosmic prisons, their theoretical opposites called white holes as cosmic fountains, and wormholes as speculative bridges between distant regions of the cosmos. These solutions suggest that the universe's structure is far more bizarre than classical physics ever imagined, containing objects governed by seemingly paradoxical rules. Understanding the most extreme objects in the universe requires grasping the foundational concepts of general relativity, which redefine our notions of space, time, and matter. The theory rests on the idea that gravity is not a force but a manifestation of space-time curvature caused by mass and energy. This geometric interpretation, combined with the principle of causality defined by light cones, provides the essential framework for comprehending how space-time singularities can form. Newton's unsolved problem of action at a distance depicted gravity as an instantaneous, mysterious force acting across vast empty voids. Einstein's concept of curved spacetime elegantly resolved this by proposing that massive objects like the Sun don't pull on planets directly but instead warp the four-dimensional spacetime around them. Planets then follow the straightest possible paths, known as geodesics, through this curved geometry, making gravity a local and causal phenomenon. The equivalence principle forms the very bedrock of general relativity by asserting that an observer cannot locally distinguish between the effects of gravity and acceleration. A person in a windowless, accelerating rocket would feel the exact same physical sensations as someone standing on a planet's surface. This profound insight was Einstein's key to unlocking the geometric nature of gravity. The equivalence principle directly implies a geometrical consequence by demonstrating that gravity affects light, a phenomenon not predicted by Newtonian physics. If an accelerating rocket fires a laser beam across its path, the beam appears to bend downwards, and therefore, gravity must also bend light. This bending, known as gravitational lensing, is only possible if gravity is a feature of spacetime geometry itself, rather than a simple force. Einstein's field equations, elegantly summarized as G equals 8T, describe the fundamental relationship between the universe's content and its shape. The matter-energy tensor, T, represents the distribution of all matter and energy, which in turn dictates the curvature of space-time. The Einstein tensor, G, quantifies this resulting space-time curvature, perfectly encapsulating the idea that matter tells space-time how to curve, and curved space-time tells matter how to move. The mathematical challenge of Einstein's field equations arises because they are a system of 10 coupled, nonlinear partial differential equations. Their nonlinear nature means that the gravitational field itself possesses energy and can act as its own source, creating a feedback loop that makes finding exact solutions incredibly complex. This complexity is why only a handful of exact solutions, describing highly idealized physical situations, have ever been discovered. Light cones provide a visual map of the causal structure of spacetime, defining the boundary of cause and effect for any given event. The cone's interior represents all possible future paths, while its exterior is the causally disconnected elsewhere. In flat spacetime, all light cones are upright and identical, but gravity causes them to tilt, illustrating its influence on the possible futures of objects. The gravitational influence of a massive object is visualized by the inward tipping of light cones in its vicinity, a direct representation of its gravitational pull. This tipping signifies that all future paths, even for light itself, are bent towards the mass. At the event horizon of a black hole, the light cones are tipped so severely that all future paths point towards the central singularity, making escape impossible. The Schwarzschild solution, the first exact answer to Einstein's equations, delivered the startling implication that a sufficiently dense mass would create a region from which not even light could escape. This solution introduced the concept of an event horizon, a one-way membrane in spacetime, and a central singularity, a point of infinite density where physics breaks down. It transformed the abstract mathematics of curved spacetime into a concrete prediction for one of the most extreme objects in the universe. In an astonishing feat of intellect, Carl Schwarzschild formulated his solution during a wartime discovery while serving as a German soldier on the Russian front in 1915. Despite the harsh conditions, he tackled Einstein's complex equations just months after their publication, considering the simplest case of a single, non-rotating spherical mass. His work provided the crucial mathematical foundation for the theory of black holes. The Schwarzschild metric is a formula describing spacetime curvature around a static, spherical mass, revealing a geometry that becomes increasingly warped closer to the object. It shows that far from the mass, spacetime is essentially flat, conforming to our everyday experience. However, as one approaches the mass, the metric's components show how both space and time are distorted, culminating in the extreme effects at the event horizon. The mathematical breakdowns in the Schwarzschild solution highlight a critical difference. The true singularity at r equals 0 is a physical reality where spacetime curvature becomes infinite. In contrast, the coordinate singularity at the Schwarzschild radius is merely an artifact of the chosen coordinate system, much like the poles on a Mercator map appear infinitely long. This coordinate artifact marks the event horizon but is not a physical barrier itself. The point of no return is defined by the Schwarzschild radius, calculated as r equals 2gmc², where g is the gravitational constant, m is the mass, and c is the speed of light. At this specific radius from the central singularity, the gravitational pull is so immense that the escape velocity required to break free becomes exactly the speed of light. Since nothing can travel faster than light, anything crossing this threshold is trapped forever. A universal fate awaits any object if it is compressed to a size smaller than its own Schwarzschild radius, transforming it into a black hole. For Earth, this would mean being crushed down to the size of a sugar cube, about 9 mm in radius. The Sun, a much more massive object, would need to be compressed to a radius of approximately 3 km to meet this condition. The journey from theory to reality requires immense cosmic forces to crush a star into a black hole, overcoming the powerful pressures that support it. For the most massive stars, the exhaustion of nuclear fuel leads to a catastrophic gravitational collapse that overwhelms both electron degeneracy pressure and neutron degeneracy pressure. This unstoppable implosion is the primary physical mechanism responsible for the formation of stellar mass black holes. Initially, black holes were widely regarded as a mere mathematical curiosity, a bizarre outcome of the equations rather than a physical possibility. Einstein himself was skeptical, believing that some unknown physical process would intervene to prevent such an extreme collapse from ever happening in the real universe. The concept of a singularity and a point of no return seemed too absurd to be part of nature. White dwarfs are the stable remnants of Sun-like stars, supported against gravitational collapse by electron degeneracy pressure, a quantum mechanical effect. However, Subrahmanian Chandrasekhar calculated that this pressure has a finite limit, known as the Chandrasekhar limit. A white dwarf with a mass exceeding about 1.4 times that of our Sun has a gravitational pull too strong for this quantum pressure to resist. When a stellar core's mass is breaching the limit set by Chandrasekhar, the electron degeneracy pressure fails, leading to a further, catastrophic collapse. This implosion continues until the star's core is crushed into an even denser state, forming either a neutron star or, if the mass is great enough, a black hole. The star's fate is sealed once this critical mass threshold is surpassed. As the next stage in stellar evolution for massive stars, neutron stars are formed when gravitational collapse becomes so intense that it merges protons and electrons into neutrons. These incredibly dense objects are stabilized by neutron degeneracy pressure, a quantum phenomenon similar to its electron counterpart but much stronger. A single teaspoon of neutron star material would have a mass of billions of tons. Oppenheimer's contribution was to demonstrate that even the immense neutron degeneracy pressure has a breaking point, now known as the Tolman-Oppenheimer-Volkoff limit. His calculations in the late 1930s showed that for the most massive stars, there is no known force in the universe capable of halting the final, complete gravitational collapse into a singularity. This work provided the first strong theoretical argument that black holes must be a natural endpoint of stellar evolution. The event horizon paradox arises from the drastically different experiences observers have of the same event, depending on their frame of reference. A distant observer sees an object slow down and fade as it approaches the boundary, seemingly frozen in time forever. Yet, for an infalling observer, the event horizon is an unremarkable boundary that is crossed in a finite amount of time. For the distant observer, an object falling toward a black hole is subject to extreme gravitational time dilation, causing its clock to tick slower and slower relative to the observer. Simultaneously, the light from the object undergoes gravitational redshift, stretching to longer, redder wavelengths until it becomes undetectable. The combined effects make the object appear to freeze and fade at the event horizon, never visibly crossing it. From the perspective of someone falling in, the event horizon holds no local significance and is not a physical barrier. The infalling observer would pass through this one-way membrane without noticing any special event at that exact moment. They would simply continue their journey, now irreversibly trapped, towards the central singularity. The resolution to the matter of coordinates paradox lies in recognizing that the original Schwarzschild coordinates create a distorted map of spacetime at the event horizon. This mathematical distortion is analogous to how a Mercator map of Earth stretches the poles to infinity, creating an apparent boundary that doesn't physically exist. The paradox is an artifact of a poor choice of map, not a feature of the territory itself. Alternative coordinate systems, such as the Kruskal-Szekeres coordinates, provide a more complete and undistorted map of the black hole spacetime. In this new framework, the mathematical singularity at the event horizon vanishes, revealing it as a smooth, traversable region of spacetime. These coordinates successfully describe the geometry from the perspectives of both the infalling and distant observers without contradiction. Penrose diagrams are ingenious tools for mapping infinity, allowing physicists to represent the entire causal structure of an infinite spacetime on a single, finite diagram. In these diagrams, light rays always travel at 45-degree angles, making the causal relationships between different spacetime points immediately clear. They are essential for understanding the global properties of complex spacetimes like those containing black holes and wormholes. Penrose diagrams reveal that the singularity inside a black hole is not a location in space but rather a moment in time. Once an object crosses the event horizon, the singularity lies in its inevitable future, just as tomorrow is an inevitable future moment for us. Within the horizon, all paths on the diagram, all possible futures, terminate at the singularity. When the Schwarzschild solution is maximally extended, its mathematics reveals a surprisingly complex topology with several exotic structures. This complete solution describes not just a black hole, but also its time-reverse twin, a white hole, and two separate, parallel universes. These structures emerge when the equations are pushed to their logical extremes, far beyond the simple case of a collapsing star. The maximally extended Schwarzschild geometry reveals a structure containing four distinct regions of spacetime, going far beyond the black hole itself. These regions consist of our own exterior universe, the black hole interior, a second exterior universe, and a white hole interior. The geometry describes two universes connected by a non-traversable wormhole, with the black hole acting as an entrance and the white hole as an exit. A white hole is the theoretical time-reverse twin of a black hole, a region of spacetime from which matter and light can only escape. Nothing can enter a white hole from the outside, as its event horizon is a barrier to entry. It acts as a source that ejects matter and energy into the universe, making it the exact opposite of a black hole. A white hole is conceptually defined by a past singularity, a point in the past from which all matter and energy within the white hole region emerge. This is in direct contrast to a black hole's future singularity, where all matter is destined to be crushed. The white hole singularity represents a beginning, a cosmic fountainhead from which a universe or region of spacetime could theoretically spring. An Einstein-Rosen bridge, more commonly known as a wormhole, is a theoretical shortcut through the fabric of spacetime. In the context of the maximally extended Schwarzschild solution, it is the feature that connects our universe to a parallel one. This bridge is the throat connecting the black hole in one universe to the white hole in the other. The Schwarzschild wormhole represents a fleeting connection that is fundamentally non-traversable. The throat of the wormhole expands from and collapses back to a singularity so quickly that not even a beam of light has enough time to make it from one side to the other. Any attempt to cross this bridge would inevitably end at the crushing gravitational singularity. The Kerr solution describes a rotating black hole, which fundamentally alters the object's structure compared to its non-rotating counterpart. Rotation drags spacetime around with it, creating a region called the ergosphere, and splits the event horizon into two distinct surfaces. Most significantly, it transforms the central point singularity into a ring singularity, opening up new theoretical possibilities. The Kerr solution, discovered by Roy Kerr in 1963, was a pivotal achievement because real stars rotate, meaning any black hole formed from stellar collapse must also be rotating. This solution provided a much more realistic and complex model of black holes than the static Schwarzschild case. It introduced new features and phenomena that are critical for understanding these objects as they exist in the universe. The ergosphere is a unique region outside the event horizon of a rotating black hole where spacetime itself is dragged along by the black hole spin. Within this region of co-rotating spacetime, it is physically impossible to remain stationary relative to a distant observer. Everything, including light, is forced to rotate with the black hole. Yes, it is entirely possible to enter the ergosphere and subsequently escape the black hole's pull, provided you do not cross the outer event horizon. In fact, the Penrose process describes a theoretical method for extracting rotational energy from the black hole by sending a particle into the ergosphere. This region is a zone of extreme frame dragging, but it is not the point of no return. A Kerr black hole has dual horizons, an outer event horizon and an inner event horizon, also known as the Cauchy horizon. The outer horizon is the familiar point of no return, beyond which escape is impossible. The inner horizon is a more complex boundary where the predictive power of general relativity breaks down, and tiny perturbations can have enormous effects. The rotation of a Kerr black hole causes the central singularity to be smeared out into a ring singularity due to centrifugal forces. Unlike the point-like singularity in a Schwarzschild black hole, this one-dimensional ring has a radius and lies in the equatorial plane. This structural change from a point to a ring has profound theoretical implications for what might happen to an object that reaches it. Theoretically, the ring singularity of a Kerr black hole offers a path to elsewhere, as it might be possible to pass through the center of the ring without being destroyed. This could allow an object to avoid the infinitely dense singularity and emerge into another region of spacetime, such as a different universe. This possibility, however, is considered highly speculative and likely unstable in a realistic physical scenario. The primary physical arguments against the real-world existence of white holes and traversable wormholes are their extreme instability and the violation of fundamental physical laws. White holes are thermodynamically forbidden as they would spontaneously decrease entropy, and the structures predicted by eternal black hole solutions are not formed by realistic stellar collapse. Furthermore, traversable wormholes would require the existence of exotic matter with negative energy, which has never been observed. The Schwarzschild and Kerr solutions describes eternal holes that have existed for all time, which is a significant problem for their physical relevance. Real black holes form from the dynamic process of stellar collapse, and this process itself likely prevents the formation of a corresponding white hole or a wormhole to another universe. The idealized mathematical solutions do not capture the messy reality of a star's death. The inner horizon instability is a critical flaw in the Kerr wormhole concept, as even the slightest physical disturbance, like a single photon falling into the black hole, would be infinitely blueshifted at this boundary. This would create an infinitely energetic shockwave, effectively forming a new singularity that would destroy any potential traveler. This instability acts as a cosmic gatekeeper, blocking any path to another universe. The existence of a white hole would represent a profound thermodynamic violation by contravening the second law of thermodynamics. This law states that the total entropy, or disorder, of an isolated system can only increase over time. A white hole, by emerging from a chaotic singularity into an ordered state of matter and energy, would represent a spontaneous and massive decrease in entropy. To stabilize a traversable wormhole and hold its throat open against the immense force of gravity, one would need for exotic matter. This hypothetical substance must possess a negative energy density, which would give it gravitationally repulsive properties. While such effects are known to exist on a microscopic scale in quantum mechanics, there is no evidence that macroscopic quantities of exotic matter exist in the universe. Observational evidence for black holes has progressed from indirect inference to direct detection, while the biggest unsolved mysteries lie at the intersection of gravity and quantum mechanics. We now have definitive proof of their existence from stellar orbits, accretion disk radiation, and gravitational waves. However, the information loss paradox and the nature of singularities remain profound, unanswered questions. Indirect evidence for black holes, like that from the Cygnus X1 binary system, relies on observing the effects of the black hole on a visible companion star. In contrast, direct evidence comes from detecting gravitational waves with observatories like LIGO and Virgo, which are ripples in spacetime itself caused by the violent merger of two black holes. This direct detection is a direct confirmation of the predictions of general relativity. The definitive proof of a supermassive black hole at the center of the Milky Way came from decades of tracking the orbits of stars around the radio source Sagittarius A. By applying Kepler's laws to these orbits, astronomers calculated the mass of the central object to be over 4 million solar masses, all confined within a region so small that no known object other than a black hole could explain it. This work, led by Reinhard Genzel and Andrea Ghez, earned them the Nobel Prize in Physics. The Event Horizon Telescope achieved a monumental feat by capturing the first ever direct imaging the shadow of the M87 black hole. This shadow is the dark region in the center of a glowing ring of hot gas, representing the area where gravity is so strong that light is captured, creating a silhouette against the bright accretion disk. This image provided stunning visual confirmation of the existence of black holes and matched the predictions of General Relativity with remarkable accuracy. Hawking's conundrum, known as the black hole information paradox, arises from the conflict between general relativity and quantum mechanics. Hawking showed that black holes should evaporate over time by emitting thermal radiation, but this radiation appears to contain no information about what fell in, seemingly destroying information forever. This violates a core tenet of quantum mechanics that information can never be lost, creating a deep and unresolved conflict in modern physics. Roger Penrose's cosmic censorship hypothesis is a crucial conjecture in general relativity that proposes all physically realistic singularities must be hidden from the rest of the universe behind an event horizon. This principle is vital for predictive physics because if naked singularities without a horizon could exist, it would randomly emit information, making the future of the universe fundamentally unpredictable. The hypothesis essentially states that nature abhors a naked singularity.